My name is Hugo. I'm a professor from the Catholic University of Minas Gerais. I'm going to present a work that my student Ana Paula and I performed at the software engineering at PUC. It's called Microservice Decomposition Evaluation using Dependency Graph and Silhouette Coefficient. Well, I'm not going to talk about microservice or monolith because it's a well-known topic. I'm going to talk about approach to microservice decomposition. We can always start, well, of course, the first approach we can't ignore is build from scratch. There are lots of advantages from building a software from scratch and redesigning it and choosing the best architecture using the most updated technology. But it's costly, usually it takes time. And many of the companies don't want to invest money in a feature that is already working. There is another well-known and working approach that is incremental refactoring, where you actually build the new features based on microservice architecture, keeping old features on monolith. At some point of time, you're gonna have like two versions of the same feature or same functionalities, but as the software evolves, you gradually translate it to microservice architecture. So these two approaches are okay, well known, they work well. But there are other approaches where you can actually get the monolith and decompose it. And I summarized it in three main dimensions or three main approaches that I call model-oriented, static analysis, and dynamic analysis. In model-oriented decomposition, you decompose a monolith based on its domain information. You actually assess which domains your software have. You have model-driven design techniques that you use to separate concerns and separate different services. Static analysis uses source code to analyze and decompose monolith into microservices. You use software that analyzes the code and make a call graph where you can see which class call each other module or each other class, and based on that you can define coupling parameters and cohesion parameters that make it possible to automatically decompose or at least automatically suggest microservice decompositions. And dynamic analysis uses runtime analysis, uses the same call graph, but it's a dynamic call graph based on which feature that calls each other during runtime to look for microservices or to look for dependencies between modules that can suggest they belong to the same microservice. So these are the main decomposition approaches: model-oriented, static analysis, and dynamic analysis. In object-oriented applications especially, we have several works that we based on to make our work. I'm going to present 4 works here. They are in chronological order. We have SBCARS. It's a very important work from 2016. They used entity relationship models to find the services, which service updates each model, so we can use this as a base for a kind of domain-based design. We had a dependency graph generation with clustering. It's Maslami from 2017. They are based on logical coupling, based on single responsibility principle and semantic analysis. So they limited the context based on domain-oriented design. So they limited the context of each microservice, saying this microservice should be inside this context. This is very good, provides very good quality decomposition, but needs a software engineer that understands well the project and understands well the domains that are involved in that project. which sometimes we don't have this software engineer. Sometimes they moved along, they moved to other companies and so on. And they used also collaborators, a list of developers who contributed to the monolith and how they contributed to it to make assumptions about connections between microservices, between units, between modules. So it's a very important work. Monolysis is also a very important work that is based in model view controller architecture to decompose software. But it's a very specific architecture that not a monolith use. Process mining is another example, but it's a runtime log-based analysis and Microservice decomposition. They use expert assessments to analyze the quality of the decomposition. The attributes they use are number of classes, number of duplicate classes, and coupling between microservices. That is a variation of the CBO, the coupling between objects, that is common for analyzing coupling of object-oriented applications. So they used a quality measure from object-oriented applications to analyze the quality between the microservice decompositions. So these approaches are very good, they are very important, but the problem that we wanted to tackle was these approaches, they use either domain entities, static analysis, user history alone, but these techniques are not exclusive. We wanted to study and to find out how can we combine and how these combinations make possible for us to have microservices that are cohesive and then have no coupling between other microservices or among other microservices. In the literature, there was room to perform decomposition combining approaches. There are not many works about that, and analyzing application artifacts in greater depth. Most feature works of these papers, they always suggest that we need to analyze application artifacts in greater depth, especially methods. They don't use methods in general, and they suggest that we should analyze methods, and we wanted to do that. To suggest finer grained microservices. That was the idea of analyzing these artifacts in greater depth. So we had two research questions that we wanted to answer. Is the combination of approaches applicable? So this is the main question we wanted to answer. We wanted to combine approaches in a way that it was not done before. And the second objective was, is it possible to use a clustering metric to automatically determine the number of resulting microservices? Actually, the second research question came from the first one. After we combine approaches, we need to set several parameters, for example, the weights of each approach, how each approach will influence the decomposition. So we need a metric, we need a way to assess these decompositions and to compare these decompositions, and so we needed a way to automatically determine how these microservices are decomposed, and if they are well decomposed, if they have a lot of intersection, how this works. So our methodology, we had the research methods we used mainly was we had a feature set that was made of classes, methods, and change history and modification history. So this by itself was a novel approach, especially because we combined classes and methods. And actually there is a kind of hierarchical change here, because usually modification history changed several files. We made a tool based on Java, and in Java each class is in a file, so modification history usually involves more than one class, and a class involves more than one method. So we have kind of a hierarchical feature set here. And we devised the new similarity measure. This similarity measure was really important for the success of our approach. We devised a way to calculate the intersection between two microservices based on these artifacts. So we chose a similarity measure, which means that two microservices that have no intersection, they have similarity of 0. So, and the similarity between the same microservice itself is 1. So how can we do this? We have alpha. Alpha means the common artifacts, common features, like alpha C is the common classes between two microservices, alpha M the common methods between two microservices, and alpha H the common history between two microservices. The W means the weights for the WC, weight for the classes dimension, weight for the method dimension WM, and weight for the history dimension WH. We divide it by the total number of classes, methods, and history of both microservices. So we calculate this similarity measure for each microservice pair, and we start joining together microservices. So we use a hierarchical clustering approach, and this hierarchical clustering starts joining together the most similar microservices, and every time we join, we calculate the similarity measure again to see if it matches the threshold, if it's below the threshold, if it's below, actually if it's above the threshold, the similarity measure threshold, we join the microservices, otherwise we keep it separate. So this is the approach for the clustering. So we made the clustering based on this similarity threshold and the similarity measure. When the clustering ends, we have several resulting microservices with several intersections between them, and that then we devised a new approach. It's also a novel approach for microservice decomposition, that to use the Silhouette coefficient. Silhouette coefficient is a well-known metric for clustering analysis assessment. It's a metric that measures how close one cluster is to each other. Actually, the letter A means the average distance between internal microservices in a same cluster. And letter B means the distance between the cluster and the closest microservice outside the cluster. So this is actually very interesting because we started the clustering with a lot of microservices that were identified from the call graph, from the dependency graph. So every method that is not called by anyone was a microservice candidate. So we calculate the Silhouette coefficient to the closest microservice candidate. So it's a very interesting approach that allows us to know if the clustering results were good. What does good means for microservice decomposition? If the Silhouette coefficient is high, it means that the elements inside the clustering, inside the microservice, are very coupled. They have a high coupling inside the clustering, and low coupling outside clustering, which is good. So we have high cohesion and low coupling without knowing the domain, without needing to know the domain. Which tools were used to perform the decomposition? So the tools were, we built a tool, actually we built a working tool. You can find it on the Git repository. In the paper there is the Git repository. The tool that we made is a web tool where you can put the URL of the Git repository and the path of the jar and the weights that you want for the classes, methods, and change history. And you can actually put a lot of parameters like which modules you want to decompose, which modules represent the microservices, and then it starts building the dependency graph using the Java call graph utilities. The Java call graph utilities make a dependency graph based on classes and methods. Then we use the JGit library to get the change history, the modification history from the Git repository. So we built another tool that actually parses this change history, and based on the diffs, you can see which files, we can find out which files were changed in each commit. And based on this file change per commit, we can actually make another dependency that links together to files or links together to classes. Finally, with these dependencies, we generate the similarity matrix between these suggestions of microservices, these candidates, microservice candidates. This is actually before the clustering, and then we start clustering the microservices based on this similarity graph in this hierarchical manner. So this is how we work, how we approach the problem. Let's see the results. We tested in 3 repositories. These repositories, since we don't want to substitute the software engineer, we needed sample repositories that we knew what was inside, that we knew how they were built. So the 3 repositories, the first one is from Ana itself, the author, Ana Santos. And she built the Canletus. The other one, the second one, is Lumen. She didn't build, but she knew the project. She took part of the project and knew the project. And Descrição Cargos is a private repository from the company. She worked in the team in the development of this project. So we could analyze the quality, we could analyze how the microservices were decomposed, and if it worked well. So these were the 3 applications that we chose. Of course, we could choose any Java application. Our tools are limited to Java, okay, for now. It's not actually limited to Spring Boot, it's just a coincidence, because Ana worked with Spring Boot. So, but it's just a coincidence, but it's based on Java, it's limited to Java for now. And so this project, they have like 80 commits. The first one, 165 commits and 86 commits. Okay, so these applications were tested, and what we did was we made several test scenarios configurations. We wanted actually, this is a research paper, so we wanted actually to systematically analyze the impact of each dimension, each element in the microservice decomposition. So we built artificial scenarios like only using a change history, only use methods, only use the classes, and then combining each other, one with another. And finally, using the 3 as a whole. So this is the main topic. This is the main result that we obtained. We can see here 2 lines. The line that goes upward is the silhouette coefficient. Actually, it's the mean silhouette coefficient, the mean and the average of all microservices. And the line that goes downwards is the number of services that resulted in this decomposition. And it's very interesting to look at these graphs because we can find a lot of things, and we can find a lot of important results, for example, if you look the x-axis, the horizontal axis, you're going to see the similarity limit, or the threshold for grouping. Since our similarity threshold, our similarity is from 0 to 1, or from 0 to 100, you can see that above 60% of similarity, we have basically all silhouette coefficients above 90%. This is really, really huge, which means that we can use the silhouette coefficient to actually control or suggest thresholds that you can see that the suggestions are low couplets. They don't have intersection. Well, if the silhouette coefficient is 1, they actually really don't have intersection. If it's 90, 0.9, they have a little bit of intersection, but it's a really low coupling. Another thing that you can see is that at some point you can see from the similarity limit of 60% that at some point the number of microservices stop decreasing. So it decides, for example, in the first scenario that uses the only change history, you can see that it chooses 8 microservices, 7.8 microservices, and then 7.4 and 7.37. You see that it doesn't change very much. We can see from the first line, the first horizontal line, the first 3 graphs, that each dimension provides different numbers of microservices. For example, change history provided almost 8 microservices in the end, while class only or methods only provided 2 microservices. And it was actually expected, since the methods are finer grained, so we have a lot of much more links between methods than links between files. So the similarities would be greater using methods. But when you combine them, you combine classes and modification history, or classes or methods and modification history, you see that, especially around the similarity measure of 50%, you have similar results for silhouette coefficient and number of microservices that were presented. And finally, when we use all of them, it's the third horizontal line, the graph alone, you can see that we kind of converged to 4 microservices on average for the decomposition. So you can see that the silhouette coefficient provided a way to analyze and visualize the quality of the decompositions. You can choose by the similarity coefficient and the silhouette coefficient how you want the intersection between your microservices to behave. If you want low coupling, higher coupling, how you want this to behave. Remember that 2 microservices, it's not actually a very big project. Some of the projects are not so good, so big. They are 5,000 lines. So, but even for that, 3 microservices are not a lot of microservices. So it's not a big decomposition result. Right? So if you want to have a larger number of microservices, you should lower your similarity measure. This is another important result that we obtained. It's the final result where we tried to see the sharing percentage by the number of suggested microservices. Usually the silhouette coefficient provides a kind of a knee-shape curve. This is not the silhouette coefficient, but usually they provide a knee-shape curve. And usually what we wanted to find here, if the sharing of classes starts to decline and stabilize at some point. And we found that at some point there's no need to increase the number of microservices. The intersection are going to keep the same. It's not actually a knee like we wanted to, like we wanted to have a more prominent curve, but we can see that around the number between 15 and 20 microservices, we have a change in the slope, and this change in the slope suggests that there's a limit of microservice decomposition. It's another way to analyze and assess how the decomposition is working. So, Microservice decomposition tool was able to generate suggestions with satisfactory coefficients, satisfactory quality. Silhouette coefficient about 75 is considered to be a very good clustering. The more specific the element is, the finer is the granularity of its suggested microservices. As I told, the change history usually changes more than one file. The class is usually lies within one file, and usually one class has a lot of methods, so that's why we have these hierarchical measures. And that's why the similarity, the intersection of methods are higher than the history. Only the silhouette coefficient alone was not enough to determine the best set of microservices. This is important to notice, to show this limitation. We can actually control the number of microservices and the coupling between microservices or among the microservices, but we can't actually choose which set of microservices are best. If the methods are best, then the history, the change history, or then the class-based decomposition. We would need a software engineering to analyze deeper each suggestion and assess which one would be better. The Java call graph utility library has limitation with the use of lambda expressions in Java. So the projects used Java 7 and Java 8. So there was not much use of a lambda expression, but it's still a limitation. But for newer versions, it's every day more common to use lambda expressions in several generics programming and so on. And this limitation must be overcome. So this is a limitation for microservice identification, the first step of the procedure. And methods that were overridden in a class that belong to an evaluated package and that are called by a class outside this package are considered to be service. This is another limitation. Since we build candidates from methods that are not called by anybody, if a method is called by a class outside the package of the monolith, we like our software didn't see it. So it didn't see that this method actually belonged to maybe a larger scope, a microservice or larger scope. So this was a limitation as well. So mainly the limitations of our work were based on the static analysis itself. Both limitations are related to the static analysis itself. And the main conclusions were, so we implemented an open source tool, which is nice, which is good to help software engineers. We don't want to substitute them. We can't find the best set of microservices. A new similarity measure was devised. This is really interesting, and it proved to be a good measure, a useful measure at least. We used the silhouette coefficient, and it was able to provide insightful information about the quality of the decomposition, because we could analyze coupling indirectly, of course, but we could analyze the coupling between microservices and the similarity thresholds, and help to define the similarity thresholds for a good decomposition. And future work, of course, demand a better analysis of suggested microservice and possible introduction of dynamic analysis as a feature as well. Since we showed that combining approaches are a promising path, research path, of course, introduction of dynamic analysis should be the next step. Thank you.